So good morning. Today we'll have the third lecture. We're looking at symmetric algorithms for confidentiality. On Tuesday we studied stream ciphers, and today we'll move on to block ciphers. So a block cipher is a symmetric cipher, which means that Alice and Bob share a secret key in advance, and then they will use it to protect information. And unlike a stream cipher that encrypts typically bit by bit or byte by byte, so modern stream cipher is 32-bit by 32-bit, but at least smaller chunks. Block ciphers operate on larger chunks. Historically, it was 64 bits. Today, block ciphers have 128 bits. And for some applications, we even use 256-bit block ciphers. So a stream cipher internally has a state that keeps being updated. And so every time you encrypt a bit or a byte, the encryption will be different because the state is different. And the state depends on the key and on initial value. And also, of course, on the time, because with every plaintext bit you process, you update your state. A block cipher is stateless. It's just a mapping that takes 128 plaintext bits and maps it to 128 ciphertext bits under control of a key. And the block cipher is reversible, so you can decrypt and go back from the ciphertext with the key back to the plaintext. So you can compare it to a library where every key chooses a book, a dictionary, and every dictionary is to a different language. And there is one, the encryption goes, say, from English to Armenian, and there is also a decryption book from Armenian to English, but there is, for every key, there is a different language. So today, 64-bit blocks, which was the standard until about 20 years ago, are being deprecated. They're still used, for example, by the banks, because every time you enter a PIN number, it's encrypted with a block cipher to 8 bytes. And so the banks all want to change their infrastructure. So they keep using 64-bit block ciphers, but today you use actually larger block lengths. We'll also explain to you in this lecture why 64 bits is not enough for most applications. And the key length we covered already in the previous lecture. So a very famous cipher, DES, has a 56-bit key. Today, in fact, you should use 128-bit keys or even 250-bit keys. So once you're above the 9600-bit threshold, you're okay. For short term at least, for long-term security, you want 128 bits. But there is no reason to have block ciphers with key length between 56 and 96 bits. This is just also legacy again. But it still exists because it's still feasible to break it. And here you'll see a number of ciphers with N their block length and K their key length. For example, Kazumi is a cipher used in mobile communication in 3G. But when the cipher is used in the legacy, in 2G, it's used with a 64-bit key, while in 3G with the 128-bit key. So, research on block ciphers started at IBM. It was a very important company in the 60s and 70s because it built the first mainframes that are, by the way, the banks still use mainframes for much of their processing. IBM did some research on this topic because there was an increased interest in use of cryptography for commercial purposes, so initially for banks. And then the US government decided to have a competition. They didn't get much entrants or candidates, and then they started the competition again, and they got a candidate from IBM. And in the end, that turned out to become the DES algorithm, data encryption standard. We now know today that it was a design between IBM and the NSA. And the NSA has admitted that they had one important decision they made. They shortened the key length to 56 bits. Why 56 bits key? Because this is a key that was good enough in 1975, 76, 77 for security, but the NSA could still break it with a key search machine. That was the decision taken. At that time, it was very hard to do cryptography. Computers were slow, and so you had to build special hardware, and chips were very small, so the whole algorithm of DES is designed to fit in 1970s hardware. So it's very tiny. And the most important thing is that the US government decided to make this public, so the whole world could see the cipher, and it was allowed to be used for sensitive but unclassified data. So classified data was supposed to be encrypted with a secret or top secret algorithm. So people were very skeptical in the beginning. The academics complained about the key length, but the solution was found for the key length problem. And more or less the banks picked it up because the US government said that it's okay. And so today in your bank card, you still have TES. Well, a very little longer key in most banks, but so it's still very important as a cipher, although it's reaching its 50 years age. So we also learned that DES was pretty well designed to resist some attacks we didn't know about, but the designers of DES knew about it. And so if you would change DES a bit, in fact, DES would become very vulnerable. But of course, the details were not leaked. They were only found out 15 years later by academic researchers who studied DES and found out that there were some attacks that worked very well on many other ciphers, but not on DES. So in some sense, there is no practical attack on DES today except for searching all the keys. There is attacks which are more efficient than they should be, but they're not really practical. So how does it work? It's not that important, but at least you have an idea. So it splits the plaintext up in two blocks of 32 bits, left and right. And it computes a very complex function of the right and adds this to the left with an XOR, and then it swaps left and right. Okay, and this you do 16 times. So the operation itself is quite simple, as we will see. If you're a hardware designer, you will see it's very easy to design this, implement this in hardware, so it fits in little hardware. You just do this 16 times, every time with a different key, and those key bits are 48 key bits selected from the 56-bit key. So in every round, you don't use 16 key bits, but you don't use 8 key bits, but you use all the other ones. So why this kind of bizarre operation of swapping left and right and adding a function of the right to the left? Well, if you want to decrypt this, what you do is you take the left side, which now becomes the right side, you take a complex function of it and you add it to the left side, and then you find this back. Now the nice thing is that the hardware for encryption and decryption is the same. So they didn't need two chips. With one chip they could do encryption and decryption. The only difference in encryption and decryption is that in decryption we start with key 1 and you end with key 16. In decryption you start with key 16, you end with key 1. So here you can see the round. I will not go too much into details. It looks very messy, but there is lots of mathematics behind. And the core component is these S boxes. This is Boolean functions from 6 bits to 4 bits. And so they were part of the controversy. How were they designed and so on? I think we now know how they were designed. But all these things have a lot of math behind them. But if you're a hardware designer, this is clearly something which is easy to implement in hardware. Like crossing wires, this is very easy. This costs nothing in hardware. It's a nightmare in software to do this. But in hardware, it was very efficient. And here's the details. So these S boxes take 6 input bits, and the 2 output bits select a row, and then the 4 inner bits are permuted, so this is a permutation of the row. So the problem is key search. So if you would write software on a PC, you could actually try a DES key in about 1 nanosecond. This is not so hard as it seems, because the fastest software doesn't implement DES as you think it would do. It implements on a 64-bit machine 64 DESs at the same time. It uses every bit of the register as a different DES, and then it does bit operations. So you kind of turn your words 90 degrees, and you completely different operations. Well, you do operations, but in fact you compute 64 DESs at the same time. If you do the math, in fact, if you have 64 PCs, so if all the students who take this course would put their laptops together, they could actually recover a key in something like a week. This is today, of course. This is almost 50 years after this was proposed. In the 1970s, there was a lot of controversy about it. And then in 93, one of my friends, Mike Wiener, made a design. And he was at that time working for a large telco. And at that time, large telcos, what they actually did was they built huge rack of hardware, and they filled rooms with it to actually switch telephone calls. Right? So he knew how to design such systems. And so he showed that if he would have had $1.5 million, he could find a DES key in 3 hours. And this kind of shocked the banks, because all the banks were using DES. And he showed a machine. And so there was like, oh, we should stop using DES. Well, the academics told the US government already in the 70s that DES was not secure enough, but they didn't want to listen. If you would build the same machine today, it would actually find a DES key in something like 15 milliseconds. Now this is a very interesting lesson occurred to me. So I was academic at the time. We were kind of shocked that nothing happened because nothing happened. So people said, interesting, there is a problem. And what then happened is that the US government told companies you can export cryptography from now on if you use only 56-bit keys. Then you're allowed to export your cryptography to the rest of the world. Because until then you could only export 40-bit keys. And then the European Electronic Frontier Foundation got really upset, and so they paid somebody, a young grad student, and he actually built a machine using FPGAs, so much less efficient than ASICs. He built a machine, it cost him $250,000, and it didn't take 3 hours, it took 50 hours to find the desk key. And so here's the machine. And so then the whole design of the machine was published in a book, because in the US there is First Amendment, you can print and say anything. So you could actually not export crypto code, but you could print a book and export that, right? Also PGP software, mail encryption software was also spread over the world by just printing a book with the software, because that's the First Amendment. Interesting, then the banks were shocked. So this is very important as an engineer to understand. As an engineer, you believe that if you explain to a banker that you can build this machine and it costs so much, then the banker will not believe you. They only believe you when they see it. It's also important if you need money from a bank for a startup or so. So banks don't have much imagination, and people who work there. They want to see the thing and then they panic. Okay? So then there was big panic in 98. What to do? And the bank said, okay, we'll get rid of single dash. It's not secure, we have to get rid of it. We'll take 5 years. I'm sure that there is still banks in the world that still use single dash today, even if they had the plan to do it, but it's now disappearing from the standards. 10 years later, people build better hardware for about $10,000, you could do it in 6 days. So the cost, of course, keeps going down and down. We also had quite some nice master thesis projects improving these designs and so on. It was clear this is actually very efficient. So finally, in 2004, so about 10 years too late, if not 15 years too late, the US government said, NIST determined that the strength of the DES algorithm is no longer sufficient to adequately protect federal government information. So it's kind of, although the paper of Mike Wiener was 93, it took the US government 11 years to say, well, you can no longer use DES. And then they said you can actually use triple DES. We'll come back to that right away. So first we go into something more technical. So IBM was very unhappy with DES, not with the design, because it's a very good design. They were very unhappy with the key length. IBM wanted a 128-bit key. The NSA wanted a 56-bit key. The compromise was a 56-bit key. You don't compromise with the NSA. They decide. So a natural thing to do is to actually encrypt twice with DES with 2 different keys, because now you have a 112-bit key, and this is very close to what you want. And now it turns out that this is not good enough. So it turns out that if you encrypt twice with DES, you have double DES, as we call it. You don't get 56-bit key, you don't get a 112-bit key, you only get a 57-bit key. You get only 1 key bit you gain. Okay, well, you can argue that this ignores storage costs. If you take into account storage costs, you gain something like 16 bits of key. Still not good enough. And why is this? Because there's an attack called meet in the middle attack. And so this requires 2 to the 57 encryptions, but quite some storage. And then later on it was shown you get rid of the storage, but then you have to do 2 to the 72 encryptions. So that's 2 to the 16 times more. And that would be feasible to build such a machine. So how does the attack work? So you first have to collect some plaintext and ciphertext pairs. In this case, we will need 2. Because if you have only 1 plaintext ciphertext pair, you have 64 bits of equations. Every plaintext has 64 bits. So if you have 64 equations in 112 unknowns of the key, you clearly will not have a unique solution. Right? It's nonlinear equations, but so you need at least 128 equations, and then you're sure that you have a unique solution for the key. So you need 2 plaintext ciphertext pairs. So what you're going to do is, we call it meet in the middle, so you compute forward from the plaintext to a middle point, and backward from the side to the middle point, and this is how you'll find the key. I'll explain you the details. So what you do is you take your plaintext and you encrypt it under all keys K1. So you run to your key to all the counters, from all zeros to all ones. So it's a huge table of 2 to the 56 entries. And in the table, you write the A value, the value which you obtain by encrypting plaintext P with the key K. This table is quite big, to the 56, because the number of keys. And then you have to store the key, which is 7 bytes, and then the A value, which is 8 bytes. So it's 15 bytes together, so this is about 960 petabytes. Today, you could actually do this if you have a good budget, but of course, when this attack was proposed, it was not feasible because nobody knew how to build some memory. What you do now is you start from C and you run to all the keys K2, and you decrypt and you find the value B. Now, if K1 and K2 are the right values, then the value B is equal to the value A. That's the middle point. And so then you know that you found K1 and K2. Okay, so you don't have to store things anymore. You just take C, you try a key 2, you decrypt, and you check whether the value you have is in the table or not. So you have to do one decryption and one table lookup in the table to check, is the value which I obtained, is it value present in the table or not? So that we call a match. So, and then you find the solution. Now, if you find a solution you're not sure yet, as we will see, there could also be, you could have had bad luck. It could be that actually a K1 and K2 match, but they're not the right key. Okay, because if you test only for one plaintext, you test 64 equations. For a 112-bit variable, there is clearly many more solutions. So to be really sure you have the right value, you take the second plaintext ciphertext pair, P prime, C prime, and you also check that key1 and you check that key1, key2 encrypts P prime into C prime. And if that's the case, then you're sure with very high probability that you find the right key. Okay, so this is easy, right? So you store a table in which you go forward, you store all the A values, then you run to all the K2s to go backward, and every time you look up is the value in the table, and if it's in the table, you may have found the solution. Clear to everybody? Okay. So the cost. So step 1 requires 56 encryptions. Steps 2, sorry, so the forward encryption, and the backward encryption is all 2 to the 56 encryptions, so the sum is 2 to the 57 encryptions. And then you have, as I said, 2 to the 60 storage. In the backward step, you don't store anything, you just look things up. So this seems easy. There is a small technical detail. So if key 1 and key 2 are correct, they're the right key, then you will definitely get a match. Okay, but you may also get a match when they're not correct. You may be unlucky. So that actually you get the same value, A and B, but in fact the keys are wrong. Okay, so we have to do slightly more analysis to make sure that we really don't do much more work. So assume, so I have my table with the A values. I now pick a K2, I find the B value. What is the chance that the B value will be in the table? Okay. Well, we know the table A table has 2 to the 56 values. So in fact, 1 in 2 to the 56 values is in there, right? Because there's 2 to the 64 possible 64-bit values, 2 to the 56 values will be in there. Okay, so one value in 2 to the 56 is there. So in fact, if I try a key K2, after about 2 to the 56 attempts, I will find a match in the table. Okay. So I have 2 to the 56 B values to compute. And in one case, out of 2 to the 8, I have to actually do an extra check. Okay. So this is 2 to the 56 divided by 2 to the 56 is 2 to the 48 extra checks. And for those 2 to the 48 cases where I have a match, I have to then check the second pair, plaintext ciphertext pair, P prime, C prime. And so in only one case, it will say yes, and in the other cases with high probability, it will say no, it doesn't match. So in fact, it turns out that this extra check is very cheap. It only takes 2 to the 48. So it's not much more work than I did before. So in fact, you get false alarms every 2 to the 56 values. You just do a second test, and then you can throw it away. But in the overall picture, my complexity has not increased. The complexity is 2 to the 57 encryptions. And that's the cost. So, because you get 2 to the 48 candidates, 2 to the 48 cases, if you try K2, you have 2 to the 56 values of K2. 1 in 2 to the 56 cases, this B value will be in the table. And then you have to test whether they also match P prime, C prime, and there only 1 to the 64 values will remain. Why? Because, well, every encryption gives you 64 equations, non-linear equations, bit equations. So the probability of a random input matching this is about 1 over 2 to 64. So in fact, you will not get anything remaining. The probability that there is a key pair remaining that's wrong to the 48 over 2 to the 64. So it's small enough. And even if you would be wrong, then you take a third pair, and then you're really sure. So it's not a big problem. Once you have 1 plaintext ciphertext pair, or 2 or 3, that doesn't matter so much. But it will not cost you much. Okay, so this is the total cost. So as we see, the 2 to the 48 encryptions don't play a big role at all. So, and as I said, I will not show the attack, but with a much more clever attack, you can actually get rid of the memory. And this is much more complex. I will not explain it to you, but with a much cleverer attack, you can do it with 2 to the 72 encryptions and only a few kilobytes of memory. And that's much cheaper because 2 to the 60 memory is really expensive. You can do it, but you also have to look up in this memory all the time, and this is very slow. Looking things up in a big memory at random can take thousands or millions of cycles. Right? So encrypting something with DES takes 16 cycles, but looking something up in memory takes millions of cycles. So this is why the second attack is actually much more practical. And so the surprising thing is that if you do DES twice, you gain only 1 key bit. If you don't count the memory, or if you count the memory, you gain 16 key bits. But it's not enough. So what do you do then? You do DES 3 times. And so this is actually what's now in your bank card called triple DES. Okay? And so we can also call it the revenge of IBM. So IBM was very upset with the NSA that the NSA chose a short key. So 2 years after the standard was published, IBM published a paper saying, hey, you can do it 3 times DES, and this is much more secure, and now your key is actually, your effective key size is much better. Now, you have to understand the real world to understand why 3 times DES, IBM decided to put a decryption in the middle. So you encrypt with DES, then you decrypt with DES, and then you encrypt with DES. So why do they do this? Well, if you make key 1 equal to key 2, then these 2 steps cancel out and you have single DES again. So in fact, you kind of, with the same hardware, you're now backward compatible with the old single DES system. As a cryptographer, this is a weakness. That if you choose 2 keys equal, that you just get single DES, that these steps cancel out, but it's a weakness deliberately designed to make sure that you're backwards compatible with all the systems that still use single DES. There is another shortcut, because in fact, you can choose 3 different keys, key 1, key 2, key 3, which is 168-bit key. But in fact, what the banks choose is key 1 and key 3 are equal. Not key 1 and key 2, that would be dumb, because then the steps cancel out, but they make key 1 and key 3 equal. And that's called 2-key triple DES, and that's actually in your bank card. So the banks published this standard. So IBM proposed this. The banks made a standard for this for transactions in 1986. 2-key triple DES. The US government refused to approve it until 2004, when they had to admit that single DES, they finally admitted single DES was not good enough. And then they said, okay, you can actually use triple DES. We now finally approve triple DES, which is an indication that the NSA cannot break triple DES because the NIST dragged their feet all along a long time, so it took them a long time to approve it. And they said, well, if you use 2-key triple DES, that gives about 80-bit security, because there is an attack. It's a very tricky attack again. More or less, it says if you have 2 to the 40 non-plain text, which is a lot, if you know a terabyte of plain text, then you can reduce a key search 2 to the 80. So the US government says 2-key triple DES is 80-bit security. 3-key triple DES, it also doesn't have 168-bit security, it has about 100-bit security, 100 to 110 bits. Okay, so 2004, the US government says you can keep using 2-key triple DES until 2009, and 3-key triple DES you can use it until 2030. So you will, when you graduate, after 5 years, your job will be to get rid of 3-key triple DES. Now the point is, which version of triple DES have the banks implemented? 2-key triple DES. So in fact, they were very angry because they implemented 2-key triple DES, and so the US government no longer approves it. Are the banks right? Yes, the banks are right, because at least in Europe, for every transaction you use a new key, which means you can never collect to the 40 plain text for the same key, which means the attack doesn't apply, which means that actually if you change your key very often, 2-key triple DES also gives you more than 100-bit security. And so the banks are right to not use 3-key triple DES. It turns out that some attacks actually work better against 3-key triple DES. But that would bring us too far. But so almost nobody uses 3-key triple DES. But the US government only approves 3-key triple DES. So this was a game in the previous century, and at still the beginning, so 2004. So DES is really not secure. So 2-key or double DES is like 70-bit security, not much better. And then 2-key triple DES is no longer valid, but it's still being used. 3-key triple DES 2030. So, but you really want something that's secure till 2060, 70, 2080. So in 1997, the US government launched a call for the advanced encryption standard. So now you also understand the name, because there was data encryption standard, and there was the advanced encryption standard. So it's not very advanced because it's now 25 years old, but at that time it was advanced because it was for long-term security. So there was an open competition. It's like the Olympic Games for cryptographers. So anybody can participate. There were about 24 designs. I think it was really funny because Deutsche Telekom sent the whole team to California to present their scheme, and I think half the cryptographers in the room broke their scheme on the spot. It was really very embarrassing for Deutsche Telekom. So IBM put in a scheme, of course, RSA, all the big names. The requirements were 128-bit block length, key length of 128 bits, no, 192 bits, 256 bits. It should be as strong as triple DES, but more efficient, which is not so difficult because triple DES, of course, is very slow. It's more secure than DES, but it's also 3 times slower. And so you should give it away for free. So more or less, key search for AES is no longer a problem. Well, you can say now on the quantum computer, maybe, but even then, the current estimates say you need about 2 to the 70 quantum gates, okay? So now on an Intel chip on the high-end processors, there is something 2 to the 32, 2 to the 34 gates, classical gates, right? Nobody knows, and of course you can put 1 million machines together, so we can build classically, we can build 2 to the 50, maybe to the 60 gates, right? But quantum gates, you know, the current quantum computers have a dozen of gates, or 100 gates, right? There's nobody who knows how you can build such a machine with 2 to the 70 gates. So in that sense, we don't worry too much about these kind of attacks. So the design is quite different from DES, because in DES you split your input in left and right, and then you only operate on one of them, and the other actually stays unchanged. So in AES, you actually apply nonlinear function and 8-bit to 8-bit mapping to every bit of the state, and then you apply a mapping, and this mapping is designed to be efficient in software. But it's also efficient on 8-bit machines, so AES is also efficient in smart cards, and it's also designed to be efficient in hardware. So in that sense, the philosophy is very different. And so what you need to know to make a good cipher is you need to know cryptography, of course, but you also have to know hardware and software. And this is why many mathematicians or people from companies who didn't have hardware experience, they failed to make a good design because they didn't know how to be efficient in hardware and software. So there is 3 variants of AES. I mentioned this already. So the 128-bit version has 10 rounds. The 256-bit version has 14 rounds, so it's 40% slower. And there is also an intermediate version that nobody uses, actually, not as far as I know. And as I mentioned, in 2003, the US government announced that AES can now be used for top secret information. Well, the 128-bit version for sensitive classified secret at the level secret, and the higher key lengths 192 and 256 can be used for secret and top secret information. So it shows that the NSA has very high confidence in the AES algorithm. So otherwise, they wouldn't allow top secret information to be encrypted with it. So it's now in everything. So the whole world adopted AES. So Wi-Fi security, AES. Authentication in mobile phone, AES. TLS security, AES. Everybody uses AES for everything. Hard disk encryption, AES. The only ones who don't use AES is the financial sector. They're still using triple DES. The only case where they change is wireless, so contactless transactions. There they actually have to redo everything anyway, and then they switch to AES. But if you do a contact transaction, it's still using triple DES today. So NIST has validated more than 6,000 implementations. So the NSA said it can be used for secret and top secret. Then 8 years ago, NIST said, well, if you're worried about quantum computers, you should use the 256-bit version only. So that's the recommendation. In the beginning, there was a lot of noise because AES has some very nice tricks to make it so efficient. There is quite some clever algebra used. And so a French Polish researcher, Nicolas Courtois, said, oh, but this is all algebraic equations. I can solve these equations. And he made a lot of noise, and some people got very worried. But we're now 21 years later, he still hasn't solved any equations. So he claimed he could do it, but he couldn't do it, not even on a small, he never managed even to do it on a small version or a reduced version. But in the beginning, there was quite some scare. Today, we know that the big problem or the big difficulty of implementing AES is if you do it in software, to do it in constant time. So it turns out that the fast way in software to implement AES is using tables. And if you do that, your tables will end up in the cache. And it turns out that depending on the value of the key, the cache values change. And if you then have access to a process on the same machine, you can look at the cache, you can actually find the key. And this was pretty devastating. There is two solutions for this. One is to implement AES kind of like people implement DES, so you rotate everything 90 degrees and you implement 8 AESs in one 64-bit word, and then you get constant time, so you don't have cache, you don't use tables anymore. That's what people do today. Or Intel said, okay, there is a problem, but we like the cipher, we will make an AES instruction. And so if you have a modern Intel processor or AMD or ARM, it will have an AES instruction. And so this makes, of course, AES blazingly fast. So how does it work? Again, you don't have to memorize or know this because I will not ask questions about it. But at least it's good to have an idea what's happening. So the 128 bits is 16 bytes, and they're divided in a 4x4 matrix. So every element of the matrix is a byte. And the operations are very simple. This makes it easy to implement in hardware, but also in software. So you have 4 steps. So the first step is sub-bytes. You will take 8 bits, and you will look it up in a table to replace it by another 8 bits. Now this function is designed in such a way that you can also implement it very efficiently with logic gates. For those of you who took my algebra class, it's just the inverse mapping over the finite field, GF2 to the 8. So it's just an inverse mapping. It's a very simple mapping, plus some affine transformation, because otherwise there would be an attack. So you mix actually 2 field operations to do this, but these S boxes are public. In software, there is a clever trick to do 4 S boxes at once. So in fact, you can implement this step not with 16 instructions if you have a memory, but you can do it with 4 instructions. On a 32-bit machine, obviously. Not on an 8-bit machine, you have to do it bit by bit. Then, very simple step, then you shift the rows. So you shift, the first row stays unchanged, the second one goes 1 byte to the left, the third one is a circular shift, of course, and then you mix the columns. So to every column, you apply a matrix vector product, and so all the bytes of the column are mixed. And so because you shift the rows and you mix the columns, so now everything is mixed with everything. This is the most tricky part. As you see, this matrix has quite some structure. It's also chosen to be simple, so there is only 1, 2, and 3 in there. And it's not integers, it's finite field, but even in finite fields, 1 plus 2 is 3, so you can actually save a lot. Multiplication is not, integer multiplication is multiplication in the finite field, so it's kind of slightly different multiplication you have to implement. But in software, you can get this for free, this mixed column, because you compute column by column, and you do the mixing in the table lookup as well. In hardware, this is very efficient to implement because you just need simple multiplications. And then you add the round key. That's it. So there is a few more details. So you start with a key of, in this case, 192 bits. So you have your key, you write it in 32-bit words. And then in round 1, you use 4 keywords. And then in round 2, well, you need, again, 4 keywords, because it's 32 bits each, so you need 4 of them. So if you run out of keywords, you make extra ones. Okay, so, and if it's a multiple of 6, then you make a complex function. If it's not a multiple of 6, you just add 2 previous ones. So it's a very simple key schedule, but you can only compute it forward. You cannot compute it backward. You can't start in DES. It's very nice. Actually, it was a clever trick of DES. You take the key, and you, for every round, you compute a new key, and when you're done, the key is back in position, so you don't need to store the key. Here, in fact, you go from the key and you transform it. So if you want to decrypt, you have to first start computing the whole key, all the keys, and then you can use them backwards. So it's a bit more annoying, but also decrypting AES is not the same as encrypting. So you have to use the inverse S-box, and you have to use the inverse mixed columns. So in fact, you need different hardware, and the decryption is slightly more complex than the encryption. That's the difference with DES. It's a design decision that was made. But as we will see, there is many applications where you use AES without using the decryption anyway. So it doesn't matter so much. So 18 years ago, people showed that you could already achieve 40 gigabits per second, and this is 130 nanometers. So today, your phone has 4 nanometers, so you can see that it would be possible to build terabits encryption. I couldn't find specifications of it, but for sure, if you would do this, if you would want to do this, you can do this. So as I mentioned, the new AES instruction came in 2010, and with this instruction, you can go below 1 cycle per byte. So encrypting a byte takes less than 1 cycle, which is really amazing, because this is faster than most other things on a processor. If you don't have AES hardware support, the fastest implementation that works on 8 AES at the same time requires about 7 cycles per byte. Now, maybe that doesn't say you much, so of course you can see it's about 10 times slower than with hardware, which is not so surprising. But if you take triple DES code, the fastest triple DES code we have takes 100 cycles per byte. Okay, so it's about 12 times faster than triple DES. So nobody in their right mind will use in software triple DES, because even if you have no hardware support, AES is way faster. You can also make it quite compact. It fits in less than 3,000 gates. And so it also fits very well in software on processors. So here you see some speed comparisons done a couple of years ago on what was then a high-end machine, but I don't think the numbers have changed so much. Of course, machines get faster, and you can reduce this. But so what you see here is speed in cycles per byte. So the more cycles per byte, the worse. How many more cycles you need. Why do we use this measure for benchmarking? Because it's independent of the clock speed, right? Because of course you have processors with different clock speeds, and clock speeds keep still improving slowly. So to have an easy to compare benchmark, you say how many cycles of the processor do I need to process a byte? It doesn't depend whether your clock speed is 2 or 3 or 5 gigahertz. Of course, your speed in megabit per second or gigabit per second depends on the clock speed, but not the efficiency of the cipher itself. And so you see that if you have a long message, then DES will be 30 cycles per byte and triple DES will be about 90. And AES, well, depending on whether you have hardware support, will be between 0.7 and 7 cycles per byte. Okay. If you take modern stream ciphers like CHA-20 or HC128, you're also at 1 or 2 cycles per byte without hardware support. In fact, if you have no hardware support, you can actually gain by using these modern stream ciphers. But there is a price to pay if you use a stream cipher. Before you can start encrypting, you have to do a setup, the initialization phase. And in DES and AES, this is 0. In CHA, this is still a few hundred cycles, and in HC128, it is 12,000 cycles. So of course, if you're going to encrypt a video of gigabytes, it doesn't matter. But if you're going to encrypt a transaction or an internet packet, then it does matter. Because a packet is a few hundred bytes, then it's not efficient. So you see that if you encrypt long messages, and you have no hardware support for AES, then stream ciphers are better. But if the messages are short, or you have hardware support, then nobody can beat AES at this moment. So to summarize how block ciphers are broken, so you can try all possible keys. And so for this, key needs to be large enough. What you could also do in theory is collect plain text and ciphertext and build a table of all the plain text and ciphertext that are corresponding. But it's clear that if my block length is 64 bits, I will need to collect a lot of information before I have a good mapping. So it doesn't actually work, it's not efficient. There is also another attack, and I will not spend too much time on this. This is more for the advanced crypto course, but at least you have an idea. What you could do is, you could take one plain text and do like in the double DES attack. You can encrypt it under all possible keys. And then you store the result. So in double DES, we only do it for half, but you can do it for the whole cipher. And if you can then convince your victim to encrypt the same plain text, then you can just look up in your table what the key is, right? But of course, if my key is 128 bits, there is no way you're ever going to be able to build that table, right? 2 to the 128 times 2 to the 3 bytes or 2 to the 4 bytes, there is not even a word for it, for the memory you would need. But Hellman pointed out that there is a very clever trick called time-memory trade-off, where you can actually do, you still have to run to the key space once, but then you do a limited storage, limited, say, for AES would be 2 to the 80 or so, which the NSA maybe could still do. And then you can recover each key in 2 to the 80, which is a bit of a concern, right? So, of course, we know that the NSA can't first run to the whole space, so they can't do it. But this shows that, say, an 80 or 90-bit key today is problematic. Because for a 90-bit key, these trade-offs would mean you run once to the key space, it can take you 2 years, but then you store something like an exabyte, and then you can find every key into the 60, which for the NSA means in a couple of minutes or so. So there is some more clever attacks, and they work for any block cipher. They only depend on the key and the block length, or any stream cipher. How it works, that's for the advanced crypto course. And there is also clever attacks, again, for the advanced crypto course that try to use the internal structure of the cipher. So in general, where block ciphers get their strength from is doing, I didn't emphasize this enough, but maybe I should repeat this. So if you look at AES, these rounds are very simple, and one round of AES is very insecure. Because more or less, if you would write it out as an algebraic equation, it's a very simple equation, and you can solve it by hand. And 2 rounds of AES you can also break, because if you can solve 1 round, you now know about the meet in the middle attack. So now you can break also 2 rounds by going forward and backwards and solving the equations. And 3 rounds becomes a bit more difficult. 4 rounds, there is still attacks, but so very quickly it becomes very, very hard. But so the best attacks, shortcut attacks on AES, can break 6 or 7 rounds, but nobody knows how to break 10 rounds, because you keep mixing things over and over and over. So that's the strength of a block cipher. That your equations become so complex that you can't even write them down anymore. It's not a mathematical proof, but so it's a very strong mixing where you keep repeating things, and a few rounds are not secure, but the more rounds you use, the better security you get. That's more or less the philosophy of block cipher design. So now, when I showed you a block cipher, I showed it to you like this. And there is a very important message that you should never encrypt like this. Although this has a name, it's called ECB mode, electronic codebook mode, which means you take your plain text, divide it up in blocks, and you encrypt block by block. Now, why you shouldn't use this? I just have an example of plain text. For your entertainment, we encrypted this with simple substitution on the left. Remember the cipher we saw in the first lecture. And on the right, I used a transposition cipher where you move bytes around. So it's clear that in this case, for this kind of information, these ciphers are not secure. So let's go for AES. Let's use AES to encrypt in this mode, this picture. What you get is this here on the left. So this is kind of shocking because AES is a very secure cipher. You can't find the key. There is no physical attack, but if you use AES wrongly, in fact, you don't encrypt much. If you use AES properly, like we use it today, you get something like this on the right, and this is how it should look. So it's more or less proper. If you really want to nitpick, what I can show is not really random, because if you show such a picture, if you put it in PowerPoint, you know what PowerPoint tries to be smart. They try to apply JPEG compression, and so they take matrices, and they try to find structure in there, which is not there. They try to find it, and in the end, they produce structure. So in fact, if you take a random picture and you compress it, you put it into PowerPoint, it becomes bigger because the compression fails, and it actually creates patterns in it. So in fact, if you're really, really critical and you really look carefully, what I show here on the slide is not random. But I have the original random picture, that you have to believe me, okay, that the real encryption is random. But it's a very big challenge, how to show a random picture in a standard tool. Of course, you can use a normal image processing tool and say don't compress, but the tools try to be smart and they fail here. But it's random, you should believe me. So this is how people used to encrypt, I would say, until about 15 years ago, 10, 15 years ago. This was the default way to encrypt stuff, called the cipher block chaining mode. I already showed you also CBC MAC in the previous lecture, or in the first lecture. So here with cipher block chaining mode is an encryption mode. It's very simple, and it solves all the problems you have with ECB. By the way, ECB mode, it's a standard, and so what happens is that sometimes some industry sector, say the electricity sector, says, oh, we need security. Oh, then they take an engineer and they say, you should encrypt this. Engineer takes a textbook of cryptography and he looks, oh, section block ciphers, open block ciphers, modes. He takes the first mode, which is ECB mode, and then he implements that. Okay, there is lots of standards. In the electricity sector is one of them where, because the engineer didn't bother to read the chapter, he just took the first picture, that they still use ECB mode. Okay, it's kind of, it should never have been standardized in the first place. So it was actually designed to encrypt keys, single keys. That's the only thing. You can only use it to encrypt one block, actually. That's okay, but not two. Okay, so now CBC mode, what you do is you take a random and secret IV. So this is different from the stream cipher. In the stream cipher, the IV was public. Here it should be random and secret. Okay? And you XOR it to the plain text. Now, if you remember the one-time path, what you really have here is encryption of P1 under the one-time path. Because if my IV is random and secret, it's like a one-time path. Right? I've never used it before, and I will not use it afterwards. So I have here a perfectly random string by applying the one-time path to P1. Okay? If you then apply AES, well, this is random, you get something random out. So C1 is random. So I can put this is my first ciphertext block. Then C1 is random. I now use it to randomize P2. So I add it to P2. Okay. What I get out is random because this input is random. P2 can be structured, but the output here is again random. It's like a one-time path encryption. It's not quite the same because in this case, the opponent may see C1 and he may actually, so it actually is not secret anymore, but at least it's random, which means it's uniform distributed. There is no patterns in it. And so what you get here is something that, well, you still may be able to guess it, but it has actually as many zeros as ones, and as many 0 ones as 1 0. It's a random string, and then you encrypt this with the key, and you get again something random. And you keep repeating this until you're done. And that's a CBC mode. For encryption, how do you decrypt? When you take C1, you apply AS inverse, so you have to use the S box in the inverse form. You have the inverse of mixed column and so on, inverse of shift row. And then when you have this result, you add the IV again and you find P1. It's like decrypting the one-time path. The second ciphertext block, you decrypt as well. And when you have this value, you add the previous ciphertext block and then you get P2, and so on. Okay, so I hope I give you some intuition that by having this random and secret IV here, you randomize this, and so this is random, and then this is used to randomize this. So it's actually a very clever way to make sure that your input is always random, and so even if my input is a plain text with picture, with structure, what comes into the AES will never have structure, will never repeat, it will actually be quite random. And then AES will encrypt it, and I will get random independent blocks, yes.
Do you have a header where you store the IV?
Yeah, so now that's indeed a very good question. So how do you transmit the IV? So, for example, one thing you can do is the IV can be the packet number, and you can have a different key to encrypt it to generate a random and secret IV, which you will really use. Right, that would be one strategy to do it. Okay, so, or you somehow make sure that the other party derives from the key a random and secret IV. That's, yes?
If the plain text 1 is not really meaningful, can I just don't know the IV and the doing this?
What do you mean by meaningful?
It feels like the only thing that IV is impacting is like the plain text 1, even in the decryption mode. So if I don't want the P1 as decrypted, I only want the P2, P3, and so on. Can I just don't know the IV?
Yeah, so if what you could also do is take P1 equal to 0, and then you can just use no IV, yes. But then there is problems with it. Even that's not good, because then it's not the same every time. It's the same every time then. So, but I think it's a very good question, because actually this is a big problem. So as we will see, CBC is a very good mode if you treat the IV properly. Now, what do most implementers do? They don't do it like this. They use for the IV the packet counter, or they say, oh, my first plain text block is not meaningful, not important. I will just use no IV, right? Or if you use the same IV all the time, if you encrypt the same plain text twice, you'll get the same ciphertext. So this is actually why we stop. One of the reasons why we stop using CBC is because implementers mess up the IV all the time. And the standards do it as well. There is another problem, which is at the end of the message. So CBC works very well, but the beginning and the end are problematic. Yes?
What happens if the IV is random but not secret?
Then there is also attacks. If the IV is random but not secret, but this is again a bit too advanced, but then you can find an attack where you actually can confirm guesses. For example, if your P1 is part of your password, I can use it to confirm guesses of the password. These kind of things. So there is lots of clever attacks that, in fact, it's clear that if it's not random and secret, there is theorems that say it's secure if it's random and secret, and if it's not, then there is always attacks. But the implementers find it annoying and difficult, and they don't do it, and the standards even don't do it. To give you an idea, in TLS, right, the web standard, the IV is the last cipher block. That's random, but it's not secret, right? But that's how TLS people decided, like all these cryptographers with their requirements. Random must be enough. Let's take the last cipher block from the previous packet and make that the IV. Very dumb, and there is several attacks on TLS that exploit this. Like the beast attack and the crime attack, they exploit these kind of things. So there is another thing why CBC mode is no longer really modern. It's serial. The encryption is serial. And today, the trick is to do everything in parallel. Also, this AES instruction of Intel, if you can pipeline, so then you can actually do many encryptions at the same time. And these high speeds I mentioned to you only work if you have pipelinable modes. So here, you can only start doing the second encryption when the first one is fully completed. And I don't know by heart, but I think at least gives you a factor 2 or 3 you lose if you use the Intel instruction in CBC mode. It will be much slower. So AES, CBC mode is really something from the past century. So it's slow, and then there is problems at the beginning and at the end. The decryption can be parallelized. So you can actually decrypt, if you have the previous block, you can also start decrypting in the middle. So if you have a movie and you've seen already the beginning, you can actually go to the whatever billion block and start decrypting. If you have the previous block, you can decrypt. But encryption you have to do from left to right. So the real problem is bit errors. So if you want to, say if you would have the idea to use CBC mode for wireless communication, for 3G or for Wi-Fi, well, that would be a disaster, because even if there is one bit error in C2, the whole block P2 will be corrupted. Because if you take AES and you change one input bit, it goes to all these mixing layers. What comes out is something completely different. Okay, even after 3 rounds, everything is different, and after 10 rounds, it's completely. So in fact, you lose this block, and also the bit error will be copied here. So in fact, if you had 1 bit error here, you have 128 plus 1 errors there. And so this is why CBC mode is not suitable for wireless, and another reason why we got rid of it, because we have now so much wireless communication. So the final problem is, what do you do if you want to encrypt 500 bits? Now, 500 bits is almost 4 blocks, but it's a bit less. So 4 blocks is 512 bits. So you're now stuck with these 12 bits. What do you do? Yes? You can put random data in there, but then that's a very good idea. But then if I decrypt, how do I know where the plaintext stops? You put the size in the header. That's what you can do. You can do that, but some systems don't like it because messages are incoming and they don't know how long the message or the block will be. So if you put the size in the beginning, which indeed some standards do, in some contexts it works, but in some contexts it's annoying because it means you can't start encrypting before I have seen the whole packet, because I put the size in the beginning.
Wouldn't that be more for stream side?
What?
If you don't know the exact length.
No, but you can also do it with AES, as we will see. So it's possible to do it, but good. So given the time, I will take a break. You get a presentation from the Capture the Flag competition guys. And you can enjoy your break. Okay, after the break, we'll continue with CBC and the other modes.